I don't know. Okay, it's working. I think we should get starting, guys. I know that this is the most difficult moment after the coffee break, especially because a lot of great networking is going on, but we have a very tight schedule. So we need to postpone all these networking activities to just the lunch break, basically, or drinks tonight if you have better plans. So I'm gonna chair the second part of the morning. It's gonna be more technology and cool young stuff that I can represent, so kind of. We start with Peter. Peter joined Calypso Technology in 2013. I think he will now introduce himself and what his company is doing much better than I can ever do. So let's start immediately with this morning.
Yeah, all right, thank you very much. I'm going to present you today some of our research findings on trying to address counterparty credit risk modelling. I sat through I listened to the previous speaker, Professor Werther, and that certainly resonated with me what was his fundamental message? Either the analysts improve their analysis or they might be looking for a new job. So this is one of our attempts to try and improve that analysis and try and capture the black swans. If you were here yesterday, one of our competitors gave a very thought-provoking presentation where they used neural networks to price barrier options. The idea being that the barrier option is very slow to price, the neural network can price it much faster, therefore reducing the runtime in their market and credit risk runs. That's an example of supervised machine learning. What we've done here is used unsupervised machine learning in an attempt to address a similar problem. So let's get started. First, a message from our legal counsel, and then just a little bit of background on Calypso Technology. It's existed since 1997, headquartered in San Francisco. It's a complete enterprise platform. It offers a solution for front office trading, middle office risk management, back office settlements on both the buy and the sell side. Most recently, there's been focuses on, of course, the cloud and also microservices, providing smaller package parts of the software. Now, just in the last 8 or 9 months while we've been doing this research, there's just been a few things that have hit the market that sort of resonated with us. Now, what we're looking at here, our focus is going to be on capturing the black swans. Now, the concept of the black swan came to prominence with Nassim Taleb in 2007, but it dates back to the 1600s. So there used to be a Latin expression as rare as a black swan, because in Europe all the swans were white. And of course, when the Europeans reached Australia, specifically the west coast of Australia, all the swans are black. So a black swan event is a jump in the paradigm, or in the market, it's a jump in the market price. So in late 2017, I saw this go down the Bloomberg wire. Traders scurry for cover as the Ionia jumps spur front-end selling. Start of the second paragraph. Traders had few explanations for the sudden move, the scale of which would normally be justified by a shift in the European Central Bank's benchmark rate. That's the definition of a black swan. It's a change in the paradigm, unexpected market event hitting. Facebook. Anyone who bought the stock in the run-up to that market high was not expecting for earnings revisions to be announced at the end of July. So Monday morning, the stock was remarked down 20%. Again, a large jump in the market, the definition of a black swan. Tesla. All right, the first jump there is when the Saudi sovereign wealth fund, when news hit the market that the Saudis were investing in Tesla. The second jump is when the CEO made an announcement on Twitter that he was taking the company private and had secured funding. Now there's a third takeaway here, and that is that the jumps cluster. Normally when there's one, you'll probably get more as the uncertainty hits the market. That third jump there is when the CEO had his televised podcast. So with this in mind, this takes us to look at BCBS-185, or backtesting counterparty credit risk models. Now, the reason I put, what we're going to do is we're going to go through that, and I'm going to show you how that really is, it essentially boils down to modelling these black swans. and it's implicit in the document. And then we're going to look at what Calypso has done to try and address that. And we're not going to use any equations, and that's been the challenge for me. Then what that's going to do is, one of the things that the machine learning did was the machine learning says, it doesn't agree with the classical modeling techniques. And so it challenges everything that's in the literature to date. And then we'll look at some key takeaways. Oh, there is a white paper. So if you do want to get into the voodoo, look at the mathematics and how this is all done, then come to see the Calypso booth. We're happy to share it with you. As you'll see there, it was written for credit default swaps. If you look at CDS time series, they display one of the highest levels of what we call leptokurtosis, or fat tails. Extreme leptokurtosis. Right? A normal distribution for the log returns would have a kurtosis of 3. Some of these CDS time series have a kurtosis of 160. They're a classic opportunity to try and model it. If you've traded credit, you know it jumps. You know it's opaque. You know there's not the price discovery you have in other markets. But what we're going to do today is we're going to look at new results that extend the paper, where we're going to look at interest rate derivatives. All right, I'm just going to put up BCBS-185 there because it's not as well known as the Fundamental Review of the Trading Book or Basel 3. It sort of lives in the shadows. But it first came to my attention when one of our Scandinavian clients we were working with on those two directives, FRTB and Basel 3, they put this in front of us and said, have you seen this? It's less well known, but it's far more insidious if you read it. In my opinion, this is much harder to satisfy than Basel 3 or FRTB, especially if the regulators take a hard line on it. Now, so let's get into what are some of the key takeaways from this document. The first one is that you must backtest your expected positive exposure model. Now, if you're an XVA trader, you know exactly what this is. All right. If you're not, well, it's essentially you run some type of simulation. You revalue all your positions into the future, and then you average all the positive mark-to-markets, and that's the expected positive exposure model. So what that leads to is, well, then you need to analyze your forecasts versus the realized empirical distribution, and that's where the problem starts. So what does that mean? Well, that means you need to look at the definition and the calibration of your stochastic processes that define your simulation model, or in other words, your Monte Carlo process. And if you're trading out to 30 years, you need to model out to 30 years, which makes it an added level of complexity. So what does that mean? Well, the expected positive exposure is made up of a number of things. One is the pricing functions themselves, that price the positions. Then you've got to look at the risk factor evolution process itself. There's a collateralization model if you have a CSA. And of course, there'll be netting and aggregation at the level of the counterparty. Now, those bottom two are fairly straightforward. They're mechanical: collateralization, netting, aggregation. There's no real room for error there. The pricing functions themselves, generically vanilla these days, and also probably validated by a model risk department if you're in a bank. So that leaves the risk factor evolution as the key part that needs to be scrutinised. Now, what I've put up here for you, this is a chart of the log returns of TECO Energy, which is an East Coast North American credit. Those 2 points at the top there, the forecast against realised values and definition, calibration of stochastic processes. The classical theory says that the log return should be normally distributed, which means that purple bar chart, which is the returns of TECO Energy, should match that red line, which is the equivalent normal distribution. So right now, if we used a log normal model, our forecasts do not match the realised returns. So if you take a classical model to the regulators for something like credit, they just don't match. And this is the point that my Scandinavian client brought to me and said, how are you going to address that? So, how can we address it? Well, Merton in 1974 was the first one to look at this problem when he said, well, let's modify my assumptions of 1972 in his seminal paper and add a jump process to the random walk or the Brownian motion. And he used what's called the Poisson process. Now, what that means, if we come back to what we're saying, well, the log returns are normally distributed. But if we add the jump process, and that's saying that some of those returns are not normally distributed. So within our time series of returns, the jumps are in there and they're not normally distributed. So we should be able to split them out. So let's try and break away the Brownian motion from the jumps. All right. Now, when I first started looking at jumps, I was talking to traders, and this was back at ANZ a long time ago in a galaxy far, far away. And I said, well, how do we do that? And he goes, well, the easiest way is just to count them. All right, just a practical trader's viewpoint. It's like, okay, well, how do we do that? So what we've decided to do is we're going to use machine learning. Now, yesterday in that talk, the neural network talk, so that supervised model, the neural network, that's a well-established area of machine learning. This is completely proprietary, this first part of a jump identification. So we had to write, there's no existing methodology I can point to for this for you. But let's just have a look at it. So here we're going to take the 5-year swap rate from 2004 to 2013. That's the data I had at the time. And then we're going to run our machine over it. So we calculate the log returns. And so now how are we going to count them? Well, if we have a normal distribution in our geometric Brownian motion, then there's certain things that time series should satisfy. You see at the top there we have, 2,247 returns, and there's a kurtosis of 6 and a skew that's not 0. Now the theory says the kurtosis should be 3 and the skew should be 0. And there are certain statistics you can satisfy that the normal distribution should satisfy, like the Jacques-Barre statistic. So basically what we did was we said, take the machine and go and find the subset of these returns that satisfies those statistics. And so this is what you get. Within that return series, there is a subset of them which satisfies those normality criteria. And so the machine finds that for us. And then what we're left with are the jumps. So the next question is, have we actually found a normal distribution on the left-hand side? So this is called a QQ plot. And without getting into the technical details, the closer the blue line is to the red line, the better the distributional fit. Now, for anyone who does empirical analysis, that would be considered to be an excellent fit, especially in the tails of the distribution. So right out on the edges there, where it's -3 + 3, right, it's bang on, and that's what you're looking for. So we can safely say that, yes, that subset of returns that the machine found is our normal distribution for our geometric Brownian motion. But then now what can we do with the jumps? And so remember we saw that Tesla chart, the jumps cluster. And so that's what we attempted to do, is to let's try and capture that event in the market in our time series. So what we've got here is what we applied is what's called hierarchical clustering. And that is a well-recognized form of unsupervised machine learning. And we used a thing called Ward's minimum variance algorithm. So basically what it does, all the hierarchical clustering does is it looks to find the closest points. And it keeps on adding points to the clusters. And it does that by saying, which point can I add that increases the variance by a minimum? And what we've then done there is you see that they're different colors. They're the actual clusters that the machine has identified. Now, what you can take away there is the clusters, and we saw this a lot with the credit default swaps, is that the clusters correspond to actual market events. For CDS, they're often actually specific events to that credit, something that's moving that credit around, but there's also systemic events. And that's what we're seeing here. So we have a long period of no jumps, where we have a very stable market after the dot-com correction in 2001. And then there's the first blue cluster as the liquidity correction in 2008 starts to take effect. And then there's a second blue cluster, which corresponds to the Lehman default. And then there's another cluster after that which corresponds to the monetary policy easing that the Fed undertook. And then there's clusters for the European sovereign debt correction. So now the question is, we've now got these clusters. What else does it tell us? Oop. The clusters capture regime switching. So by looking for to control the variance in the clusters, what we've got is we're capturing different volatility regimes in the market. So this is all very promising, all right? But the next question was, well, what do we do with it? Now I know I've got this new information on the market. I've got new insights into what's driving the market, and I've quantified it. So when we first started working on this, I'd say to traders, I'm looking at capturing clustering in the market. I find that CDS jumps cluster, and they go, well, of course they do. It's like, well, yeah, but it's a bit more than that. We have to find a quantitative technique that we can use to model that. And so what we want to do now is we've now got the information, but what can we do with it? we're coming back to our counterparty credit risk model, we now have to project that through time. Right? We have to simulate into the future and mark our positions. So what we then did was we took the clusters and then calibrated what's called a Markov chain to build a Markov chain Monte Carlo, and also to calibrate our jump process. So underlying this in the mathematics, rather than having, say, one jump process for the entire time series, we've now got discrete jump processes for each cluster. So we've got a much deeper and richer parameter set. And so then you run the simulation. And this is an example of one path. Now remember, in a counterparty credit risk for BCBS, you'd run 3,000 simulations, maybe 5,000 simulations. This is just one path, okay? So what do you see here? Well, the first thing is that at the top chart there is the triggering process for the jump. So you have to have something that says when the jumps occur. And what we've used here is what's called a Hawkes process. Now they date back to the 1970s. They were originally designed for earthquake modelling. So if you think about earthquakes, living in California as I do, when there's an initial earthquake, and then there's often aftershocks. So the earthquakes cluster. And so Hawkes built this process to try and capture that clustering. The Princeton School has recently, in 2014, applied these Hawkes processes to the same problem of triggering jump clustering. So if you go and look for those papers, you'll find them published by the Princeton School of Economics. What we've done is, well, we've used the same Hawkes process to trigger the jump clustering, but then our calibrated clusters to actually modulate the size of the jumps. All right, so what we see down there, again, the different colours correspond to different clusters from the Markov chain. So we start off with a long period of no jumps, just like we saw in the original time series, and then a large cluster, and then some smaller clusters. Now, of course, every simulation is different. This is just one example. Now, crucially, and this is the big result, is that how does our jump cluster distribution match the realised data, which is what Basel is asking for? The answer is reasonably well. So again, the closer the blue line is to the red line, the better the distribution will fit. In this case, the lower tail, the bottom of that chart, is almost exactly a match. The upper tail still shows a little bit of deviation, but still, by any empirical standard, that's a very tight fit. So by applying the calibration cluster by cluster and enriching the parameter set, we're able to get a much better match to the actual data in the marketplace. Now, what did the machine learning think about the classical modelling assumptions? So what I put up here just a list of the general models that are used in the market, from Merton to Merton 74, which is geometric Brownian motion plus the jump process. Then you go to Wassercheck, who use mean reversion, Cox, Ingersoll, Ross with a square root, which can't model negative rates, which we're going to look at. But what you see there is almost no interest in modelling the jumps apart from that Merton paper. And that comes back to what Professor Werther was saying in the previous talk. You know, we need to improve our analysis. He's not saying he wasn't saying don't build models. He said improve the models. And so the next thought was, well, these are all the classical models, and when we did the analysis on the CDS, the problem we found was that the machine learning for more than half the data set, we ran it on 1,652 time series, credit default swap time series with more than 8 years worth of data. For half the names, it couldn't solve for an underlying Brownian motion. So the machine came back and said, I can't find it, it's not there. I can't find a subset of returns that match the assumptions of these models. So what we did was he said, well, just discard it. Don't use it. Just model the jumps using our cluster exponential distribution, which is a fairly big statement, right? There's some fairly impressive names on that board, and we're saying that they don't have it right. So then the question is, well, CDS is a little bit more of is not as well known as rates. So can we find an example in the rates market that shows the same price action? And the answer is yes. The Fed funds rate. There's no random walk here. There's no Brownian motion. This rate moves when the Fed moves, and we can see that. There's easing after the equity correction from the dot-com bubble burst in 2001. Then we have tightening leading into the liquidity correction in 2008, and then you can see at the end of the time series they're in another tightening cycle, and it moves like a step function. So what happens when we turn the machine learning onto this? Well, again, the model comes back and says, I can't find a Brownian motion in there. There's nothing that looks log normal. But it happily models the jump. So within that time series, it finds a jump time series, and again, we get the regime shifting in the volatility. Our QQ plot again, our blue line matches our red line quite closely. So we have a good distributional fit. I'd like to see improvement in the tails. That's an area of ongoing research, is how can I get that blue line in the tails to match even more closely. But if you use one of those earlier models, the red line and the blue line are like orthogonal to each other. There's just no relationship. It looks like that. Remember the purple distribution versus the red line? There's no... So if we come back to what Basel said, right, you've got to prove that your model matches the realized returns. Right? And so I believe if we took this to a regulator, we could get it signed off. And then we can run the simulation. So again, here's an example of one path. So before, with the 5-year rate, we had discrete clusters with long periods of no jumps. Now it's happily modeling the entire time series as one big jump process. Now it found, on this particular path, we have 1,300 jumps. The original time series has 1,700. Remember, you'd have to run 2,000-3,000 simulations. So some simulations will have 2,000-3,000 jumps, some will only have 500 as it builds out the entire distribution. If you look at the simulation at the bottom again, the different clusters are coloured based on whichever cluster it's come from that was identified. And so what that is, again, that's the Markov chain Monte Carlo, which says which cluster am I in? Am I staying in the cluster or am I moving to another cluster? All right, and that's all driven by the calibration that we did from the actual realised time series. Another example. So this is the overnight rate from Japan. The reason I bring this one up is because we have negative rates. All right. Now, in my experience, the response to negative rates has been, well, we'll use a shifted log normal model, which is basically to take log normal, which can't be negative, and pick it up and move it and force it to be negative, which creates a mixture model. But what we can do here is, again, abandon the assumption of log normality and just model the jumps. So to capture the negative rates, I can't use log returns anymore because I can't take the log of a negative number. So we use absolute returns, just one day minus the previous day. And again, the machine is perfectly happy with that. It identifies the jumps, discrete clusters, and again doesn't solve for it abandons the classical modeling assumptions. All right, in summary, we investigated this for trying to address BCBS-185. So the idea we would take this to the regulator, show them this is, and of course this model is actually a bolt-on to the classical models. It's just that some of the time it says don't use the classical models. So it's an extension of what a bank will typically already have in place for its Monte Carlo simulation. But what else could you apply it to? Well, the Hawkes process and the clustering would also work, say, modeling defaults directly. Or you could model prepayment risk for MBS, ABS with this model. Remember, the key part of a prepayment model is what's your weighted average spread and where is the interest rate. So now you've got a different way of moving the interest rates around, which hopefully would be able to address, say, the jump in Ionia that we saw in 2017. So in summary, what we've tried to do here is to move the thinking on what you need to do to backtest counterparty credit. Now, obviously, from a commercial perspective, what we're trying to do is build a model that no one else has and then lock them out and essentially move the bar up. How did we do that? We applied 3 levels of machine learning. One, to filter the time series and say, there are the jumps, there's the Brownian motion. The second, to cluster those jumps so we can replicate the price action that we see in the marketplace. And then the third was to use Markov chain Monte Carlo to propagate those jumps and exactly what we've captured into the future in our simulation. And the final result, we don't agree with the classical academic models anymore. And any questions?
Hi, Vince Goss from Prudential. So, if those jumps are caused by paradigm shifts, in policymaking and other, maybe more politically driven factors, how do you account for that in the future simulation of jumps and what those paradigm and political shifts might be?
Yeah, what you're getting at now is now the risk manager has to step in and make a decision. What am I going to calibrate to? So coming back to CDS, if you read the white paper, there's 5 examples of CDS in the white paper, and we can say there's a systemic event and there's a cluster for that. And so, for example, for that TECO energy, the biggest cluster is actually in early 2001. When the regulator stepped in and said you're not matching the standards for power emissions and you have to update your power plants. So there was a lot of interest in their CDS because there was a lot of stress in the company. So then the question is, you've now got this idiosyncratic cluster. You've got the systemic cluster. Do you want to put all of those in your simulation? You can. A common thing that a risk manager will do is pick his time series, or where do I want to start the model. So, for example, in clearing, they'll use 5 years of data plus a 2-year stress period. So there's still a bit of choice there in terms of what you want to calibrate to. But if you take the whole time series with the idiosyncratic and the systemic events, then the Markov chain will then randomly assign to those different clusters, and so you'll replicate the actual market events into the future. So it'll pick up the idiosyncratic cluster, so whatever's particular to this stock, and it'll create a cluster for that, and then it might jump to a systematic cluster and it'll propagate that. But again, you'd have to decide what you want to calibrate to. But one of the things we found was it's not always the Lehman events that's the biggest cluster, especially in CDS. It's the idiosyncratic, the things that are attacking that particular stock that are often the most volatile events. So there's another insight, is you can say, well, I need Lehman, but I want to capture these idiosyncratic events which are actually more volatile.
Till Sherman, Oliver Wyman. I think the results you showed us were all in-sample fit. Should we worry about out-of-sample and overfitting to in-sample? How would you think about that?
Well, overfitting, I forgot to mention that. And that was actually one of the comments yesterday in the machine learning sessions. I was also very cognizant of that. So in the research on the CDS, we compared our cluster calibration to a more classical calibration. So say the calibration out of the Princeton paper. And out of the 1,600 time series, or something like 1,500 of them showed an improvement in the distributional fit. So almost every single name benefited from the cluster calibration. So is it overfitting? Well, if every single name shows an improvement in the calibration, I would argue that it doesn't. In terms of how many, so there's another. In the actual model itself, the number of clusters is determined by what's called a gap analysis. Again, there's papers published on that. So I'm not arbitrarily determining the number of clusters. It doesn't generally produce 100 clusters. It typically ranges from 5 to, say, 17. So 17 clusters is going to produce a lot of parameters. My experience of using Monte Carlo, there's always time series that are problematic. But generically what I've seen, and in the paper there's actual charts. And what we do is we plot the root mean square error, which is essentially looking at how far does the blue line deviate from the red line. And almost across the board we get really good distributional fit and an improvement on the Princeton model.
Any other questions? Otherwise, I'm not here to put pressure on you, but I think we have to conclude. Okay.
All right, thank you.
Thank you. And then for this second main discussion here, we'd like to introduce you to Professor Dr. John Hausman, the president and co-founder of John Hausman Enterprise. He's a global political risk consulting firm. He will talk about the world in the US and the US in the world, which I think is per se quite a fascinating title. So let's see what the perception that Europeans, Asian people have about the United States.
Actually, I'm going to talk about that, but like all speakers, I'm going to say whatever I want. So just to give you, because it will tie into that, and I hope to end with that, and that would be a nice ending. And I enjoyed listening to the last presentation because it's not something I know anything about, and I think it's always interesting to try to look at risk in a very different way than I do. I just finished a book, which is a great thing to do, and I had 3 years to write it, which is a long time. Usually you do them in about a year. I've written 14. And 3 years, you get to write pet sounds. You get to do it the way you want. You get to go over the ending 16 times until you have it exactly the way you want. And I have a very understanding publisher at Princeton University, and it helps that he's the director of the press. So basically, if Daddy wants it, Daddy gets it. And as a result, I could make this book be exactly the way I wanted without any compromises to the editorial people, to a co-author, which you always make compromises. And there's a chapter in the book that I'm going to use to discuss what we would call Waltzian systemic analysis. Please don't be bored. The way we're going to look at it instead is a far more interesting topic to me, and it's how the book began. Why did the Beatles break up, and why did the Rolling Stones stay together? It's an important point here. You have to actually have a sense of humor about this. This relates very much to systems, and ones that are stable and not. Almost every geopolitical risk problem at present can be put down to people looking at the world in a way that it's not. My basic problem with American neoconservative thinking is they assume the world is unipolar. The world of the Pax Romana, Mare Nostrum, as they said, RC, about the Mediterranean. There's you and there's nothing else. Well, if there's just you have a certain way of dealing with that world, policing that world, making that world work. But if the world isn't the way that you assume it is, you're going to be wrong over and over and over again. We forgot in Iraq there were Iraqis. And we could blow up their army in 3 seconds. Governing the country is not so simple.